Welcome to qnawire.
So insects are pretty amazing. And maybe this is kind of creepy, but what we have is some data on a jumping flea from the early 1970s that was taken with a high-speed video camera. And the graph, just to cognate what the graph shows, is the acceleration of the flea as a ratio compared to g. So g is just 9.8 meters per second squared. And on the x-axis, this is a time graph showing that acceleration. So basically acceleration versus time. And how we're going to be answering some of the questions is we will need Newton's second law of motion, which says that the net force acting on an object is its mass times its acceleration. Ordinarily, that would be a vector relationship. We are told, however, that this flea jumped pretty much vertically straight up. So the acceleration in this case is acceleration in the y direction straight up, and the F net is a one-dimensional quantity, impelling that flea upwards. So the questions have to do with what force does the flea experience initially, initial net force, and then the maximum F net. And we can certainly answer these questions if we identify those points on the graph, and we also have the mass of the flea. So let's go ahead and write down the mass of the flea is 210 micrograms, which is let's see, is it 10 to the minus 6 grams or 10 to the minus 9 kilograms? Let's see. Yes, it is 10 to the minus 9 in terms of kilograms. So let's get everything into the correct units. Okay, so doesn't weigh much. So let's identify the points on the graph that we're looking at. The initial force can be found if we know the initial acceleration. The maximum force can be found if we find the highest acceleration. Okay, so that's the initial, and that's the max on the graph. And I'm reading these off, let's see, I'm reading this as about 140 Gs, which is pretty impressive. And the beginning I'm reading as about 65 Gs. And I will point out that a human, we would have been crushed way down close to zero with maybe 5 Gs if we're suited properly. So it points out that insects really have a different anatomy than we do. So we'll take our mass of our bug, 210 times 10 to the minus 9 kilograms, and we will multiply by the acceleration for the initial value, 65 times 9.8 meters per second squared. And that should give us the force in newtons. And it won't sound like a whole lot, but seeing that it's coming from this little flea's legs, it won't be surprising that this is a small amount. And we can do the same for the maximum force. That's the same calculation, essentially, but using the 140 Gs. So we take the bug's mass. So we're simply doing that calculation times 140 times 9.8 meters per second squared. And we will get the force in newtons. Let's see, and that's 2.9 times 10 to the minus 4 newtons. Okay, yep. So the nice thing about purporting these accelerations in terms of g is we can see how much force the bug can produce with its legs compared to its weight. So the factor of 65, for example, means that the bug is producing 65 times its weight in order to get that force. That force. It's actually producing a little bit more, but not much more. And in the case of the net max, Fnet max, that force is 140 times the bug's weight. Okay, now if you're going to do kinematics, you'll want to know how fast the bug is moving by the time it reaches its maximum force. And so you're thinking of generating that leap. And after that maximum, basically the bug is in free fall up in the air. So to estimate the initial speed, what we're going to be using is the definition of acceleration. And this is a kinematics thing. It is the change in speed over the change in time. And we're going to have to kind of reverse this and say that acceleration times delta time is equal to delta v. And that may not look very useful because we have a changing acceleration over time. But what this equation is basically saying is the change in speed is the area under acceleration versus time. We are going to approximate that area. We're simply going to take our two endpoints and join them with a straight line. So we make kind of a triangle there. And we're going to be off a little bit. We're only estimating here. But the area is of course, the area of that triangle. And so it's the base times the height, and we need to estimate the base. So the base is the time at which the maximum occurs, and we'll estimate that. Time max, kind of just eyeballing it, it's a little bit less than 1.25 milliseconds. We'll call it 1.15 milliseconds, just to have something to work with. And so the change in speed from that graph is equal to the maximum speed minus 0. We're assuming the flea is jumping up from the ground with no speed to begin with. And it's 1/2 the base. We'll call that 1.15 milliseconds. Times the height, which is an acceleration quantity, basically the 140 minus 65 Gs, which will be in meters per second squared. And working that out will give us the speed, the final speed in meters per second. We'll have units of 1/2 squared canceling with seconds. And I will do one more check on my numbers, but it is pretty impressive for this little thing. It's approximately, I'm getting a little bit over 40 centimeters per second, 0.42 meters per second. Yeah, and that's pretty impressive for a little flea.